I'm Michael Saunby from the University of Exeter, and I'm going to be talking about the VespAI or Asian Hornet project at the University of Exeter. Let me just share my slides. Okay. Oh, okay. Can you see that?
Yeah, sure. Thanks.
Good, good. Okay. So, as I just said, I'm Michael Saunby of the University of Exeter, and I'm going to be talking about the VespAI Asian Hornet detection project on the Raspberry Pi. So this began in 2021, and through 2021 and 2022, researchers at the university trained a computer vision model to accurately detect the presence of the invasive Asian hornet. And then I joined the team in 2023, and through 2023 and 2024, we've refined the model and also developed a self-contained system using the Raspberry Pi. So this talk is going to focus on the work done to achieve a robust and reliable Raspberry Pi based system that can be used by beekeepers and others to provide Asian hornet surveillance, hopefully from early 2025. So, a little bit about the team. There are the main scientific work on this is actually being run out of the Penryn campus. So, Exeter University has a number of campuses, um, and there's one down near Falmouth, so Penryn near Falmouth in Cornwall, which is where the Environment and Sustainability Institute is based. So the scientists there that are primarily entomologists studying insects are Professor Juliet Osborne, who led the project, and then we've also got Mario Recker, Peter Kennedy, and Thomas Oshiawela, who've been doing the science and a lot of field work around this project. None of them are computer programmers or data experts. So the university makes use of a team that's based in Exeter. So there's a team of research software and analysts, so sort of data science experts as well as software engineers. Um, and Stephen and myself have both contributed over the last couple of years to this project. So I won't tell you the details about everybody else. If you want to go and find out more about them, you can do. My name's Michael Saunby, and I'm currently a research software engineer at Exeter University. I have many years of expertise in scientific software design and development. And as I said, I've been working with the VespAI project last year and this year. So I was primarily tasked with helping the team turn their research into a product. So a little bit of background. When I joined them, they already had something. It was Raspberry Pi based. They were collecting images, sometimes still images, sometimes using video recording. And by that means, they had collected a lot of images of hornets and other insects and trained a machine learning model, a vision model, and it worked. What they discovered using field work in their field work was that it works best if they're able to keep any visual noise out of the system. So they were actually using a sort of an opaque baffle over a large area where they were putting bait down for the hornets. Um, and you can see in those images there that they were able to connect to the Raspberry Pi and they could see what it was detecting and they collect more data and sort of prove that the model worked. So it works. Um, what we have now is something that is pretty close to being a usable product. About a dozen of these, maybe slightly more, have been made now. So that this is a sort of a 3D printed um, camera enclosure. It's smaller than the original sort of um, ad hoc baffle arrangement that they've got. So the idea was to make something that was more compact and more portable. Um, but building on that knowledge that to maintain the accuracy of the system, they needed to keep out visual noise. So what you see on the right there is effectively the view that the camera gets, and then rather than drawing over the hornets, we've just got a little map to the top right, which shows where hornets have been detected in that image. And then we also have a web app that's running on the Raspberry Pi and a Wi-Fi hotspot, so that you can connect to that and control the system. So we're no longer SSHing in. We don't have to do any sort of Unix commands and so on. It's just done through a little self-contained web application. So I just put a little video together. This was around the last time that we were actually seeing hornets here. What I should say is that most of the hornets that you will see in these slides aren't the invasive Asian hornet. So if you see these and think, oh, I've got those at home, this is just the common European hornet. So I actually recorded this out by my garage, where there's actually a hornet nest at the end of the garage, quite conveniently. And this, what you can see here is that every few seconds it grabs a new image. In use, the system doesn't work at this rate. If you were watching a live system, you wouldn't see it refresh. You probably see it refresh about once a minute. But it's a bit boring watching that. So you can actually see the hornets moving. This kind of work, capturing images at higher speed, was also done to try and work out how frequently you do need to collect images in order to not miss any hornets arriving at the system. Although more importantly, that was done with Asian hornets rather than the European. Okay, so that's what it looks like. So did we succeed in turning research into a product? Yes, I think we have. There's still some work to be done over this winter, but hopefully we'll have something to use next spring. We wanted something that could be used by beekeepers. It should almost be an appliance, something that you can just plug in and go. But there's always more research needed. So it also needs to double up as a research instrument, something that can be used to collect more data and help refine and test models. And although for the most part, the people that expressed an interest in having something like this wanted effectively to do surveillance in their own local area, there's definitely a need for some kind of early warning system for the UK of hornets arriving. So this system hopefully can play that part by using linked systems that can share notifications and create a network. So what hardware are we using? Well, obviously, keep saying this, we're using a Raspberry Pi. The reason for using a Raspberry Pi is kind of more to do with the evolution of the project, if I'm honest. So the first field work was actually done using 64-bit Ubuntu desktop running on a Pi 4. And that was a very effective tool for that work. We wanted, in turning this into a product, to see if we could get it running on smaller devices, and we have successfully run the code now on a Pi Zero 2W. The performance is limited, but it can run the model, providing we convert it into a form that will work on a 32-bit processor. We've also run it, and this is our kind of like our chosen system for a lot of the development at the moment, is the Pi 5. Pi 5 is nice because a real-time clock's included. You need to add a battery, but that's not a problem. We're using 4 GB Pi 5s because they were the first to be released. It would work fine on a 2 GB, I'm sure. Also, because of the history of the thing, collecting data was done using USB cameras, and actually sort of GoPro clones were used quite a bit for collecting data because we need a lot of images of hornets in the early stages to train it. So we've stuck with USB cameras rather than using the Pi camera. It's not. I would say it would be worth it if you're anyone building something similar to this. You probably want to think about using a camera that has sort of lower power requirements than USB. The USB cameras have been fine. We've had to look at different cameras and review them to get cameras that have got similar optics to those that we used with the initial model training. And we fitted real-time clocks to all of our systems, primarily to ensure that the photos are correctly timestamped. So if we're collecting data and creating sort of information about where hornets have been seen and when, then you need them to be accurately labeled. We've also used the Witty Pi, which is an interesting hat, probably slightly overpriced really for what it does, but it combines a real-time clock with power management, which means it's easier to have the thing running on battery and starting and stopping automatically. Okay, so a little bit more about the 3D printed bait station. The hornets are attracted to the camera with a sugary solution. So the bottom part of the device you'll see is actually a reservoir where you unscrew a cap and you pour a sort of a diluted syrup into that. If it's going to be used around places where there are bees, so if you're a beekeeper and you're putting this near where there would be bees, it includes a bee deterrent. So that means it's attractive to wasps and flies and so on, but unattractive to bees. It's designed to provide, like I've said earlier, images without visual noise. So it's got a diffuser around it and a cover over the top to keep any sort of falling objects, rainfall and whatever away from it. So when it came to building the software, we kind of knew we wanted to create something that would effectively be a product. So one of the decisions that I made fairly early on is that let's treat this right from the outset as though we actually have a product. So rather than installing upgrades from the internet and so on, we decided that we would create each of our test releases as an SD card that we would just boot and run a completely installed system from that without having to install and configure anything else. We also need to save some data. We at the moment continue to save data on those cards. It might make sense if you were using it for primarily for data collection to actually use a USB memory stick to collect the data on. But so far we've had reasonable success with collecting data on the cards themselves. Something that probably many of you have encountered already, I found very useful for doing this, is PyShrink. It's a simple bash script that will run on a Unix system. I run it in Docker, and it's able to take the 32-bit card image and remove the empty space in the disk image, and then once we've gzipped it and so on, we've typically got something around 5 GB that we distribute. So when this goes off for the scientists to do their field testing or whatever, they just have to download it. Typically we're using Google Drive for this. They'll download it. And again, just sensible engineering practice. Make sure that these have got unique names. So we tend, rather than giving release numbers and whatever, just have the date on which the image was created, so we can know that we're using the latest one, or if we're not using the latest one, we know why we're using it and what we're doing. all of these now using Raspberry Pi OS Lite. We've moved away from Ubuntu, and we haven't used the 64-bit system for um, probably 12 months now. Okay, we know that this thing is to act like an appliance, a product that we can just plug in and switch on. So the obvious way to configure this is to have the software running as a service. Um, and we're expecting to have this running continuously, detecting hornets and recording detections fully automatically. So the actual vision pipeline is packaged up as a service, and we just use systemd to manage those services. So we'll typically the startup of the system, this isn't typed in interactively, this is done by the system when it starts up. It'll do some setup stuff. It'll then stop the setup service, start what we call the VespAI service, which is our vision pipeline, and that will then start collecting images and processing them. So we actually have three principal services that make up the system. So there's the vision pipeline we call VespAI. We've got a setup service, which prepares the system for use, sets the real-time clock, checks storage space, and allows the user to set some things up like the name of the system and so on. And then we've got a monitor service, which can be run in parallel with the VespAI service, the vision pipeline. And this allows the user to connect to the system using the hotspot and check that it's working, see any saved data and so on without interrupting the vision system. The first couple of iterations of this, we would just power the system up and leave it running continuously. What we have done since then, but primarily to conserve power when the system's running on battery, is to actually have a number of system states that we move around, and we have a cron tab which just schedules these things. So it sets the time at which the system will actually start collecting images, which in this diagram here, it's set as 6 a.m. So during the summer, that would be typically when it would start. It would start at 6 a.m. It would wake up, the vision system would be started, and then at 9 p.m. it would sleep. We've got this facility to do other things during the day. So they're not shown in the cron tab there, but you can configure it to do other things during the day. So you could actually have the Wi-Fi off for much of the day, bring the Wi-Fi on so that you can connect to it and check the system, and then turn the Wi-Fi off. So you might just have a window when you're using the system interactively, and you can save power by not having that run all the time. Okay, the vision pipeline was built using YOLO v5. There are more recent versions of YOLO. So if you're looking to do something similar, or you want to train a model for the Raspberry Pi, we found this very effective. If you go to the Ultralytics website, you'll see they've got a V8, I think, and possibly even later versions that have come along since we started this project. YOLO stands for You Only Look Once. You've probably seen lots of these images around where objects are labeled in an image. And what you're actually seeing is the end result of some post-processing. When the model is applied, it actually creates huge numbers of these rectangles where it gives the various probabilities of it being all sorts of different things, and then a certain amount of post-processing is needed to select the actual most likely candidates. But as they claim, fast, accurate, and context aware, it certainly has proved to be very effective. This purpose, the initial data collection and training with images of Asian hornets, mostly collected in Jersey, where Asian hornets are unfortunately quite common these days. They're rarely seen in mainland UK, which is the point of this project, to try and keep them out of the mainland, but they are seen in Jersey. So over 2,000 images were collected, and they were separated into two target classes, because actually having European hornets, Vespa crabro, as a target species means we can easily test the system in environments where those hornets are present, which, for Devon and Cornwall, they're quite a commonly occurring insect. Um, and that's kind of the end result of that, really, is to show that where the hornets are present, it can identify the hornets and it can distinguish between the two species with pretty good accuracy. So one of the tasks that I had was to try and get this pipeline working on a 32-bit machine. It's actually very simple. Um, it's probably, once you've figured out what to do, it's just a few minutes work to take a 64-bit model and convert it into a 32-bit TensorFlow light model. But you've got to check your results. Just because it can be converted from one form into another doesn't mean it's going to produce the same outcome. So actually quite a lot of work was done to be sure that the results we were getting were the same. And one of the things that I did to help achieve that was actually to containerize the 32-bit ARM code. So the rationale for that was there was little point in testing something that wasn't the same as was going to be run on the Raspberry Pi. So we needed to test what would be run on the Raspberry Pi. Obviously, we could have tested it on Raspberry Pi. We did do some testing on the Raspberry Pi, but it was interesting to check whether we could repeat that validation on another platform. I was actually using an Intel MacBook, and so it's emulating the ARM processor, and it was running the code. So it actually runs slower on the MacBook than it does on the Pi 5. But you can do it, and you can just set up jobs to check that all of the images are correct. I was so impressed with the Docker container way of packaging up the vision pipeline. We've actually stuck with that. So at the moment, we still use Docker on the VespAI service. So this is the script that actually runs the service on the Raspberry Pi, and you can see here that to collect images, so to get frames from the camera, we're using FFmpeg, and then we've actually got a Docker container that is running our VespAI code, which is Python code that uses the TensorFlow Lite library to give us this 32-bit system. What we also have is some follow-on stuff here, so that if hornets are detected, we've actually got our notification being sent off on the web. I'll talk about that later. So that is just running continuously. The web interface for setup, and when you're running the system, we need a Wi-Fi hotspot, because it's likely that the system will be used in environments where we can't connect to the internet. So the system comes up and you can connect to it. Once you've connected to the hotspot, you can open up VespAI local, and that will give you a web interface to the system. One of the things that we do here for new systems is just to check that the clock is correct. We actually display the date and time twice. So it's showing the date and time that's taken from the browser, and we also show the date and time coming from the Raspberry Pi. It also means that you don't have to get someone to enter in the date and time when they're setting the clock. If those two are different, it brings up a little alert. You can hit the set current time button, and it just copies the time from the browser to the Raspberry Pi to set the real-time clock. We can also check that the camera's working at this point. So that's basically all you need to do when you're setting the thing up. There's other things that you can do. I've not shown those because you might want to set it connecting to a local Wi-Fi system or whatever. But typically, you start the thing up, check that the clock is set correctly, and then check that the camera is working, and then you hit that bottom button where it does start detection, and away it goes. Once it's going, if you connect again, you get a different interface. So it's very similar. try to keep it much the same. So it's, again, showing the date and time just in case there's an issue there. Um, and then it tells you that VespAI is running. You can stop that and restart it should you wish to. Generally speaking, you don't need to. It just does its thing, and then at the bottom it will show an image if there has been a detection. It'll show you when the last detection was, and that's it. There's some more stuff in there where you can access a table of detections. There's a database that's recording the detections and so on, which is more about when the system's being used in sort of a scientific role where you're using this to collect data. Um, we wouldn't anticipate systems being deployed that people were getting an endless stream of detections. If you're getting a lot of Asian hornets visiting a site, then something needs to be done about it, and the nest found and destroyed. So the primary purpose of this really is to give a warning that Asian hornets are present. Okay, ideally the system should be capable of running from batteries. This is most likely to be a USB power bank. Now, Raspberry Pis aren't an ideal choice for battery powered devices, but you can do it. Um, the way that we've gone about this is only run necessary software. We power down at night, and we've also reduced the clock speed. I know most people that use Raspberry Pis are familiar with the idea of overclocking so that you can get higher performance out of it. I've found that actually underclocking can actually get a few more hours out of a power bank. And by slowing down the image capture, particularly if you're using a Raspberry Pi 4 or 5, um, they can capture images I showed you earlier, under a second. You could go even faster, maybe. Um, but we established that taking images every 30 seconds or so, it would be unlikely that you would miss any hornet visit. So that's the rate that we chose. Um, I suspect that in the future, it'll be even longer intervals because if you're running the thing for 12 or more hours a day and hornets are visiting, then you're going to catch them if you're scanning probably even every couple of minutes. It's all very well sort of taking a guess at how much you can say, power you can save. Something I discovered this summer, which has proved very useful, is if you've got a smart plug that can monitor power consumption. If you've got a modern GAN power supply and you plug it into one of these energy monitors, it gives a very accurate measurement of instantaneous power consumption, um, and also gives you quite a good idea of sort of the average power consumption. So you can see there, this is a little test that I did just to see what happens if I crank the detection rate right up. So if we're running at sort of 1 second intervals or whatever, then power consumption on a Pi 5, even with the underclocking, is still coming in at sort of 7 watts, whereas we can get down below 4. I think you can slow it down and get something like about 3.5 watts out of on a Pi 5. Might be even lower on a Pi 4. I'm not sure. Um, so yeah, useful little tool because you can just leave it running, set up a different series of different experiments that run at different times, and then come back and see how much power is used in different modes. So, okay, we want to save power by turning off at night. I showed earlier that that's done with a cron tab. We're not actually, because we want this simple user interface, we don't write cron tabs at all because they might change. What we do instead is have a little Python program that will write the cron tab for us. Um, I named this Power App. It probably needs a more imaginative name. What this does is it has a number of sections. So it's a YAML script. The first part is just the cron tab. So you've got to have more lines in here. It's a simplified form of cron tab. The first bit tells you the state that you want to go into, and then we just have the time to go into that. So at 7:10, it should go into the wake state. And I can look here, and wake is restart the VespAI process. So it's restarting the vision pipeline. It's restarting the monitor app because we decided we want to keep the monitor going, and we're going to stop the setup app. We don't want the setup app to be running. So that's what happens. So it means that we don't have to write a number of different sort of shell scripts and things. The Python program reads this YAML script and writes the various scripts and so on for us and updates them when they need to be updated. So the web interface just changes the times and so on in this configuration file, and then everything else is done by these scripts that are generated automatically. As well as controlling what the system is doing at different times, we now have a need to send notifications and so on. So that was some of the more recent work that we've been doing, is sending notifications. We want to combine that with ensuring that the hotspot's always available. So we want to keep to our original vision of an appliance that you plug it in, you start it up, and you can connect to it using your mobile phone. So whenever the system is powered up, it will initially go into that Wi-Fi hotspot mode to allow users to connect to it. If you don't connect after a few minutes, what will happen is that it will try and connect to your local Wi-Fi. So if you've given it connection details for your Wi-Fi, it'll connect. And that's just done using NMCLI, which is a great tool for managing sort of command line control of Wi-Fi. Again, we don't do it directly. So we have another YAML script, bit more detail in this one. So this one also carries the details of the hotspot. So our default hotspot is called VespAI hotspot, and it has a password of vesp. So we pretty much don't change that, but a user could change that. They have the facility to change that in the web app if they do wish to. And then if you've got local Wi-Fi, you can set that up here, and you just in the web interface you will set the password and SSID for the Wi-Fi, and it will manage that connection. So much as the Power app had its cron schedule at the top and then the various states, that's mirrored in the Wi-Fi app, where it has the Wi-Fi configurations in the top, and then lower down we have the various connection configurations in there. So we have, to turn on our hotspot, it'll run that script line. So it runs these commands. And then we've got a more complicated one. This is what I use at home for setting up the system, because sometimes I like to use a wired Ethernet, and I want to make sure that that's available and so on. So you can have any commands you wanted there, really, to start the system up. And what we also have now is a cloud-based notification service. So this is a service, again, Dockerized. It's a container that's running on Google Cloud Service. So what this does is provides like a web type interface to the system. And the Raspberry Pi, when it makes a detection, will actually notify that detection by posting the image to this notify endpoint. So it posts the data, and then when we receive that data at the cloud service, it will create an image which contains the original data that was sent, and then a little map to show what notification information came from that particular Raspberry Pi. This is quite sparse. I suspect in the future we'll add more information to this, so we'll have the location, maybe even a map to show, where in the UK the Hornet was seen and whatever, so that people managing this. So typically it would be bee inspectors, people have responsibility to protect beekeeping in the UK would look at these and be able to see what had been seen and check, yes, that really does look like an Asian hornet. In this case, they're not Asian hornets, these are both European hornets, and so on. And then Yeah, endpoints for the service. We've got generate report and send mail, and this automates the generation of these reports and so on. And this is running every hour. Or it runs every hour during daytime, of course. Um, and so it will send off to responsible people the details of any Asian hornets that have been seen. What we don't have yet, but I believe we should be working on, is getting SMS alerts, because some of these systems will potentially be deployed in locations where there isn't internet availability, and we might not wish to use 4G. We have got some systems now that have got 4G capability, um, but SMS would use less power, which means they could be they're left unattended for longer. Um, the downside of that is at the moment we're still in this crossover between it being a research project where we want to be verifying all of the information collected and a true um, early warning system. So at the moment, it's important to also get the images to be able to see what the system has detected and whether it really is an Asian hornet. But I think we're becoming more and more confident that the system doesn't make mistakes or rarely makes mistakes. Um, so that's kind of me done. A few acknowledgements here. I won't read those out, but happy to take any questions on this now, if there are any.
The other day, on the TV, I can't remember which channel, they were on about the checking the DNA of how they were swarming to different locations across the south of the UK. Is this anything to do with it?
It's all connected, yes. So one of the important parts of this system is this kind of non-destructive nature. It locates the presence of hornets. So we know that Asian hornets have been found. Um, and so you can see here they've got these just for anyone that is interested. I know most of the images I've been showing you have been European hornets, but the Asian hornets actually have yellow legs. If you look there, the rear legs are yellow. And in fact, in some parts of the world, I think in America, they don't call them Asian hornets; they call them yellow-legged hornets. So that's the part of the distinguishing features of them. You can see there's a sort of a darker black body with these yellow legs. Yeah, because we're only collecting pictures of them, but we're able to timestamp that and let people know very quickly that hornets have been seen. It's then possible to go out and try and find the nests. And some members of the team have actually this year, as part of their field work, went out to parts of the UK where Asian hornets had been seen in an attempt to find the nests and collect those so that they can be DNA tested. I think the key thing that they're wanting to know there is whether they are new arrivals each year or whether they're overwintering. It's known that in Jersey they're overwintering, but there's been no evidence, I think, so far, not that I've heard of anyway, that any have overwintered in the UK, or they didn't overwinter in the UK last year, but there's always a risk that they will once they start arriving.
Brian, the question?
Yeah, you're obtainers. The reason that they take
I didn't catch that. Someone will have to repeat what was said.
So, so the question was, when you're using containers, why you're using not using 64-bit instead of 32-bit?
So that what was it? Why we were using the what? So the original version that was used 2 years ago was a 64-bit system on a Pi 4 using Ubuntu, mainly because it provides that sort of research environment where you can run a web browser, do different editors and things like that. And the decision was made to try and target smaller devices. So use the Pi Zero, where it would just be easier to run a 32-bit system, and it's quite effective.
Pi 02, you can run 64-bit, of course.
You can, but it doesn't. We did try that. You can't run Ubuntu on it. There just isn't enough memory for it. So it's that compromise. We made the decision to run 32-bit. I would actually be interested in trying to run the vision pipeline on a pure microcontroller, an Espressif, or I've got some Sony SpreeSense as well that don't have an operating system and that would just run the TensorFlow model in a 32-bit environment, because it would be a sort of a lower power solution. Because in the end, what we're looking for here is not performance. We're not trying to do vast amounts of AI processing. If anything, I think another power saving thing here would be to not analyze every single image. At the moment, we analyze every single image that comes in every 30 seconds. But if that image is unlikely to contain a hornet, so we could do some simple comparison with the previous image. If there's nothing there to analyze, then why go looking for hornets that aren't there? So it would be interesting. At the moment, the system only runs for about 3 days or so on batteries, but it would be nice to be able to run it for sort of like a fortnight or so. Although, to be honest, if you've got insects present, the bait reservoir runs out in about 2 or 3 days anyway, because they drink so much of the syrup.
Right.
Yeah, Michael, have any of your detectors been stolen yet? And what do you do about getting secrets like these Wi-Fi credentials?
We haven't had any stolen that I know of. I don't think we've even managed to lose one, which is often what happens with university equipment. They just gets left somewhere and someone forgets to go and get it back. But yeah, we appreciate that the potentially that they're a desirable thing, but I think it's just what it is. They will be used in places where there is a certain amount of human presence. I don't think they actually need to be put out in woodland and whatever. They don't need to be away from habitation. Where Asian hornets have been spotted in the UK, they've often been spotted in people's gardens. People are spotting them, around the flowers in their gardens and things like that, or even coming into houses. So hopefully, the project will continue without having to risk having lots of equipment stolen.
I was wondering, so these detectors, they always have to be near a Wi-Fi hotspot then, so that they can't really be more than about 200 or 300 meters away. Is that right?
They don't have to be. It's really convenient for the development work if they are. So I have one next to my garage where I've got Wi-Fi available. But where you haven't, and a lot of the field work has been done with systems that have no Wi-Fi connection, and you'll use the mobile app. I didn't show you this, but you can use the mobile app and it will actually download any detected images. The reality is, of course, that most people will probably never detect. Ideally, you never detect an Asian hornet. So you want to check that the system is working. So you'll go there with your mobile phone, you'll fill up the liquid to make sure that insects are being attracted. You'll check with your app to see whether any hornets have been detected. Most likely it'll be no, but if they have, you can then download that information and send it off. So you can just collect the information using a mobile phone and then send an email message to say we've detected an Asian hornet here, and off that goes. So it doesn't have to be, and the device is designed around this notion that it can be entirely standalone, and you just use the Wi-Fi hotspot to connect it to a mobile phone.
Oh, I see. But I'm wondering how you might get an early warning then if you actually have to sort of go there with the mobile phone to be nearby.
Well, it's an early warning in the sense of beekeepers during the summer are generally checking their hives. They're going out to their apiary every couple of days. The university apiary at Exeter, the beekeeper through the summer, there's a beekeeper there most days. A lot of kind of professional setups where people are. We've had systems placed at farms and so on. There are plenty of places where people are working outdoors and are able to check these daily. So the alert would probably go up within 24 hours.
All right, thank you.
So Peter has signed up. Or do you want to go ahead?
Sorry, can people sign up to have one? I think the location of these will be determined by likely risk. So I think it's going to be along. I think Kent and Southampton areas have both seen some activity of Asian hornets. Other places there's been sort of spurious sightings. So I imagine next year there'll be plans drawn up over the winter to decide where systems should be located in the spring.
Can I ask?
Just going to allow people to press one or build their own.
But I think a few people have already taken the information that we've shared on GitHub and attempted to build their own systems. There's nothing to stop you taking the model that's available and building your own system to meet your own particular needs. And I'll be honest, I don't think you actually need to fully recreate the camera environment that we've used. You might get some noise and some of the occasional false positive, but probably only in poor light conditions. When we've had false positives, it's been around dawn and dusk, where perhaps a butterfly wing has just the strange shape on the edge of a wing has caught the thing and it's given a false positive. But they're very rare now.
Answer your question.
Hi, Michael.
Hi.
I wanted to ask, how are you monitoring your Docker services that you're running, anyhow, on the Raspberry Pi?
Oh well, so I'm not the Docker service on the Pi is no, we're just trusting that maintaining that that pipeline service and restarting that if it fails is sufficient. I'll be honest, the Docker part of it has been very robust. The thing that's occasionally caught us out is the camera, the USB camera. If you power down at night and then when you power up in the morning, in the summer, if it's actually quite warm and bright when the camera first comes on, we seem to have an issue with the camera sort of whiting out. But a couple of cycles around. So what we've taken to doing is actually changing the script slightly in those conditions to power down the USB port and power it back up again, and that does it. But we've had systems now that have been running continuously for months when they've been mains powered, and just the act of shutting the thing down at night and starting it up again in the morning seems to keep it quite clean, and yeah, the services do their thing.
So Moha asked this question in the chat, just saying the 4 to 5 watts is rather thirsty. He's wondering about whether or not there's better cameras out there that would use less power. In the chat, there's got a further long question there.
I'm gonna have to look in. Let me have a look in the chat. I can't. Can I stop sharing? So what's the 4 to 5 watts? Very rather thirsty. Yeah, it's not. It's the Pi that's using that. But having said that, probably half a watt is being used, maybe even a watt is being used for the camera. Um, have we considered thermal cameras? It's a kind of it's an interesting issue around using AI to detect things because certainly the scientists that I'm working with pretty much insist on a high quality image that they can verify that the thing is what the AI system has claimed it is. And I don't know of anyone that would consider themselves to be competent to identify different types of insect using thermal camera images. Um, but it's an I think that in a with the use of AI in sort of IoT devices, I can see that absolutely being the way that things will move, and that maybe it'll be achieved by simultaneously taking color images that a human can sort of look at and go, yes, that's an Asian hornet, and then also collecting the infrared images or thermal images and whatever. Um, I know that there was an enthusiast that was doing something interesting around this where they were collecting sounds and trying to identify Asian hornets from the buzzing. They make a different buzzing noise to other, all insects have distinctive sound, um, which is fine, but you would also need at the moment the image to verify that because there aren't the people with the expertise to say, yeah, that's definitely from its sound an Asian hornet.
Can I ask a question? What about running these on solar power? They only
Yeah,
work during the day.
yeah. I think
So
once they start being deployed, if we find that there are people that are able to deploy them in sites the way we want to deploy them where there isn't power, I think that's more likely that we'll go to using solar than actually really trying to get down to a really low power device. But you could do it low power. The other thing is you could separate the two things. There's no reason why you couldn't have a very low power camera taking images every 30 seconds and then sending that by Bluetooth or whatever to another device where it does have access to mains or whatever to then do the AI processing. So you could divide the problem up into a series of physically separate pieces and do it that way. But that's not the approach that we've taken so far.
In terms of deployment, I've got a question. You did say you've got a list of institutions or places to send them to. How have you determined this? Who did you get to use, say, the beekeepers who would have this? I know you mentioned Kent and
yeah, so in the UK, beekeeping associations are regional, and there's also government bodies respond. I'm not the expert on this, but the there are government bee inspectors who have existed for a long time. There have always been these appointed bee inspectors whose job is to inspect beehives to check for notifiable diseases and whatever. So it kind of falls under their remit of protecting bees from disease and so on, although this isn't really a disease. So bee inspectors have been trained up to identify the not just identify the hornets, but also use techniques to locate the nest. So what they'll do, and we've actually had people using the VespAI system for this, that once they've detected a hornet, they'll catch it, they'll paint a colored dot on it, and then they'll check for the time it takes for the marked hornet to return. And from that, they can make an estimate of how far away the nest is and start looking for nests in the vicinity. And you could imagine that being something that the unit could itself start to help with by looking for colored dots on hornets and giving you the times and so on. So we can automate some of that process of finding the nests. So it's kind of it's within the responsibility of the project to sort of like try and make these systems available where they're needed, but the decision as to where they're needed will probably be made elsewhere.
Thank you.
Do you think there'll be an option? Oh, it's weird having here come out the speaker. Do you think there'll be an option for people to print their own and make up their own devices to join in the network?
I think you absolutely could print your own. I think the unit that we have at the moment is hugely over-engineered. Really, it's a beautiful thing and it's very robust. And we've had no problems with these through the summer, but they do cost hundreds of pounds to manufacture. So I think you can achieve something very similar with sort of opaque plastics and whatever. So I'd be nice if something came out of the hobbyist community to create a cheaper but effective housing for this. But I think the 3D designs will be shared at some point. I think that will happen. That there will be information available. But it is, like I say, it's quite a complicated thing. That the top part has actually got a 3D printed screw thread where you can unscrew it and reattach it, and there's the reservoir underneath and so on, which needs to be you need to contain the liquid, so you can't have a leaky. A lot of 3D standard 3D printed material is kind of leaky, so you need to have the right sort of materials for it. But there's certainly no intention to keep this information private, so it will be shared in due course, probably early next year.
It was really good talk, Michael. Very interesting. Lots of good questions, and yeah,
Well,
really looking forward.
Thank you for inviting me. Yeah.
What happens next? We had I think it's called the Fairball Society or something like that. There's a group that sets up looking for meteorites, and they sort of use a bunch of these to detect where the meteorites are. So it's a very similar type of approach, but they've crowdsourced it all, so people can build their own and into the network. So looking forward to seeing what happens with the Hornets. Very cool. Thanks very much.